In this session, we will discuss about power MOSFET. You already know what is that MOSFET, metal oxide semiconductor field effect transistor. These are majority carrier devices. So here you can observe that this is the N channel MOSFET, this is the P channel MOSFET. In N channel MOSFET, arrow mark is inside. In P channel MOSFET, arrow mark is outside. So here you can observe that here you have drain, source as well as gate terminal. Here also you have drain, source and gate terminal. And here now you can see this is shown with a dotted line. This is also shown with a dotted line. And also here you can observe that when MOSFET is turned on, current flow from drain to source. Voltage is applied between gate to source to turn it on. Here if you want to make this one turn on, you have to apply voltage in between gate to source terminal. When you apply voltage in between gate to source, then it will get turns on, then current start to flow from drain to source terminal. And also, what is the difference you can find in between BJT and MOSFET? Here no turn on and turn off speed is high. In BJT turn on and turn off speed is low. So because of that there you will get some delay. So that will be having a low frequency, but this one will be having high frequency. This MOSFET will be having high frequency. So because of this one only you will leave this one in chopper as well as inverter. You know what is that inverter and all. In your home application during emergency, whenever there is no power at all, in that condition, immediately in order to avoid the disturbance for your operation, that inverter has to perform its operation immediately without any delay. So because of this you will use inverter. So here no for MOSFET no drive circuit is very simple. For BJT no drive circuit is somewhat complicated. Here it is very simple. But it has a very high on-state resistance. But if you compare this one with the BJT, no, in BJT whatever the resistance is there in between collector to emitter terminal. Here no in BJT you have collector terminal and emitter terminal. In between this collector to emitter terminal, whatever the resistance is there, no, that resistance is very high. But in this MOSFET, in BJT that is low. But in this MOSFET, no, in between this drain to source, whatever the resistance is there, no, here you can observe that in between drain to source, whatever the resistance is there, no, that resistance is very high compared with the BJT. So because of this one only it has maximum on-drop resistance. Because of this it is used for only low power applications. Next we will see what is the structure of MOSFET. Here you can observe very simple structure of N channel enhancement type MOSFET. In enhancement type MOSFET, no, you don't have any channel in between source to drain. You don't have any channel. Channel means this region. In this region there is no channel at all. So this is a N channel, means it is called as an N channel means when you apply positive voltage to the gate terminal, what happens? It attracts. When you apply positive terminal to gate terminal, it attracts electrons toward this. Then electrons are accumulated below this gate region. Electrons are accumulated below this gate region. So because of this there will be a formation of channel in between source to drain. Because of this channel, current start to flow from source to drain like this. So we'll see what is that structure and all. So because of this it is called as an N channel. Here there is a formation of N channel below this gate. If electrons are accumulated, why can call this one as a N channel? You know that in this N region, electrons are the majority charge carrier. Obviously, in this substrate, in this p-type body substrate, usually holes are majority charge carriers because of accumulation of more number of electrons below this gate. This portion of the region start to behave as a n-type material. So it is called as an n-channel. Next, we will see what is that. Here you have source. Source is connected to n plus region, and drain is also connected to n plus region. Here you have metallic contact. This source is not directly connected to this n plus. Here you have the metallic contact. Here drain is also connected, not connected to this n plus region. Here you have metallic contact. And in this region, above this one, SiO2 layer will be present. Here you can have SiO2 layer. Above this SiO2 layer, you can have metallic contact. From this metallic contact, gate is connected. And we will see what explanation they have given. Obviously, you know that in this n plus region, doping concentration will be 10⁻19 per centimeter cube. In p body region forms the channel between drain to source. Just we have seen in that p body region only there will be a formation of channel, n channel in between drain to source. And in that p region, doping concentration will be 10⁻16 per centimeter cube. Then there is a insulation of SiO2 layer between gate metal and p body region. And we have seen that when you apply positive gate voltage, then there will be accumulation layer will be formed. Because of this accumulation region, n channel will be formed. So to make that n accumulation layer, you will apply voltage in between gate to source, VGS you will apply. Then current IDS start to flow from drain to source. If VGS equal to 0, then the channel get absent. There is no flow of current. So because here you can observe that just now I told you that if you apply voltage in between gate to source, then it will be positively charged. Then it will attract the electrons. Electrons are accumulated below this gate region. Because of this, there is a formation of channel in between source to drain. Because of this channel formation, current start to flow from drain to source. In case if you make VGS equal to 0, obviously this is not positive, this is 0, obviously it will not attract the electrons. Then whatever this electron accumulation layer is there, that will become absent. Obviously then this MOSFET get turns off. Here you can observe that. In between gate to source you have connected the voltage supply. Electrons are accumulated below this gate region. Here accumulation. Because of this p region, type body region, this is the p type body region. This is converted into n layer. Induced channel of electrons will be formed. Then current start to flow from drain to source. Like this it will start to conduct. Next we can observe what is the advantage of this MOSFET you can find. On state resistance of MOSFET is reduced. You can reduce the on state resistance somewhat by making some arrangement. Width of the gate is maximized, hence gain of the device is increased. Obviously gate is maximized means there will be formation of a channel, then current start to flow like this. Next we will go with the VI characteristic of the MOSFET. Here you can observe that along y-axis they have drawn ID, along x-axis they have drawn VDS, ID versus VDS. Fine, you can have the curve like this. So it represents that if you want to make this MOSFET turn on, what you have done, you have applied voltage in between gate to source. This graph itself tells that VGS means you have applied the voltage in between gate to source. If VGS is less than some threshold, here you can observe that whenever VGS is greater than threshold, then only it start to conduct. If it is less than threshold, then it will works as an off switch. It will be in a cutoff region. It works as an off switch. When VGS is greater than threshold, then it will be in an active region. Then whenever VGS increases more, then it will switch from active regions to saturation region. In saturation region, you know that it works like a on switch. In cutoff region, it works like a off switch. When VGS is greater than VGS threshold, it will be in on state. Next, we will go with the switching model of the MOSFET. Here you can observe that we have gate, drain, source. Here you have the capacitor. In between gate to drain, you have the capacitor, that is CGD. In between gate to drain, you have the capacitor. In between gate to source, you have another capacitor, that is CGS. In between drain to source, you have the capacitor CDS. Obviously, there will be a junction. In that junction, there will be accumulation of charges. It start to behave like a capacitor. That capacitor is nothing but a internal junction capacitor. Next, there will be internal resistance RDS, small RDS. Actually, here you have shown this one with a small letter R, means it represents that it is the internal resistance in between drain to source. Next, current device you can show. With respect to this model, now we can observe switching characteristics. And also in this graph you can observe that BVDS means this is the voltage, up to this much of voltage your MOSFET can sustain. If you increase your drain to source voltage, this is the VDS. If you increase your drain to source voltage more than this by making your VGS off, in that condition your MOSFET will be damaged. Means how much voltage your MOSFET can able to handle, which voltage in between drain to source voltage it can able to handle without any damage. That is nothing but VDS. Next, with respect to this one, we can observe turn on time, T on. It is the sum of delay time plus rise time. Turn on time is nothing but it is the sum of delay time plus rise time. What is this delay time? It is the time required to charge that junction capacitance. You have seen that in between the gate to source there will be a junction. Whenever that junction capacitance is reached to its peak value, then only then current start to increase. Here we can observe that in the graph. Here you can observe that the capacitance, which is that is a gate to source, this capacitance need to be charged. To charge this capacitance up to threshold voltage, what is the time required? Now you can call this one as a turn on delay, TD on. If your voltage you have applied that is more than threshold voltage, then only it start to conduct. After this voltage, drain current ID starts rising. Before that it will not rise, it will be utilized in order to charge this capacitor CGS up to threshold voltage. Next, rise time means nothing but it is the time required to conduct, or it is the time required to increase your drain current from threshold voltage to up to some peak voltage. What is the time required? Now you can call this one as a rise time. Here you can see the time required for this charging is called as a rise time, from threshold voltage up to peak voltage. How much time that is required, they call this one as a rise. After this rise time, then this ID start to conduct with a full value. Observe that during this period drain current rises to its full value I naught. I naught means this is the maximum current that can able to transmit. Then MOSFET is said to be fully turned on during this period. Thus total turn on time of this MOSFET is nothing but T on is nothing but TD on plus TR. Here you can observe that behavior in this graph. When you apply VG, gate voltage VG, then VGS will not be increased suddenly. Suddenly means it should need to increase like this, but it is not increased. Why? Because of the presence of junction capacitance VGS. Just now we have seen, no? Time required to reach VGS to up to threshold voltage. How much time that is required, na? That is called as a TD on. Time required to increase VGS from 0 to VT, that time is called as an time is nothing but delay time. After this VGS reaches to VT, no, then your capacitor, gate source capacitor voltage start to increase from VT to up to peak voltage. VGSP means peak voltage, gate to source peak voltage. It will increase. You can call this one as a rise time TR. When it is charged with a rise time TR, no, then only your ID current start to flow with a maximum value. Then during turn on also you can observe that you have done this V gate voltage 0, but it will not be 0 immediately, because this is the time required. Here you can see TD off means with respect to this turn on, you can explain this one in reverse fashion. How? From maximum peak voltage above this one, what is the time required to decrease from maximum voltage up to peak voltage? That is the TD off. After this, what is the time required to decrease this voltage from VGSP to up to VT? You can call this time duration as what? For time. Fine. So with respect to this one, you can observe that ID is increasing. Here, no, whenever it reaches to peak voltage, then only it start to conduct with a maximum. Then immediately it will not goes to 0, it will take some time duration. How much? TD on plus TF. And also it is not charged immediately. How much time it is required to charge to full value? TD on plus TR. This much of time. This is the switching characteristic of your MOSFET. Switching frequency will be high. What is the meaning? Turn on and turn off period will be very less in your MOSFET. So because of this one, you are using your MOSFET in which application? In chopper as well as in inverters. So next we can see what is the advantage of having this gate drive. So what type of gate drive circuit you require? A gate drive means what? To make your MOSFET on, no, whatever the voltage you have applied in between gate to source, whatever the voltage you have applied in between gate to source, regarding this voltage, no, whatever the explanation they are giving, that is nothing but gate drive requirement. We'll see what type of gate drive requirement you are expecting. Gate drive circuit for the MOSFET should satisfy the following requirement. Gate to source input capacitance should be charged immediately. Obviously, if that gate to source capacitance is charged immediately, means what advantage you will get? Whatever the TD on, delay time required during turn on, that can be avoided if that capacitor is charged immediately. That requirement you are expecting. MOSFET turns on when gate source input capacitance is charged to full level. Obviously, whenever it is charged to full level, then only it start to conduct maximum ID. So means TD plus TR, you want to avoid that. Turn off MOSFET, to turn off MOSFET quickly, negative gate current should be sufficiently high to discharge the gate to source input cap. Obviously, during turn off, you have seen there are two type of delay, TD off plus T off. That two delay can be avoided. These are the requirement you are expecting in gate drive control. Obviously, in order to do this one, what you need to do, you will apply one capacitor. What is the advantage if you apply capacitor means? Let us consider that you are applying voltage source like this. Actually, if you don't connect this capacitor, no current start flow from this A point to R1 to this gate terminal. Obviously, this voltage is not enough to avoid this turn on delay. So what you do, instead of R1 path, you will select this path. Means if you provide like this, no, peak voltage will be provided. It will charge that gate to source capacitance immediately. So TD on delay can be avoided using this setup. During turn off also, you want to decrease that TD off plus T off period. You want to decrease this, then what you need to do? That time duration can be avoided. How you can avoid it? By connecting R2. Means that capacitor will be discharged immediately through this path R2. This is the gate drive circuit. Like this, then you can do the arrangement. For BJT also we have done this same type of arrangement, so that BJT can be turned on immediately, it can be turned off immediately, so that you can increase the switching frequency. Here also, to increase the switching frequency of the MOSFET, you have done this type of arrangements. So we will see what are the merits of MOSFET you can have. It is the majority charge carrier. Majority charge means in N type, no, electrons are the majority charge carriers. So in that one, with help of electrons only it will conduct. If you consider PNP, no, in that case, in PNP transistor, majority charge carriers are holes. No, using holes only it will conduct. So it is a majority charge carrier. MOSFET have positive temperature coefficient, hence their paralleling is EG. MOSFET have very simple drive circuit, just now we have seen. It has short turn on and turn off time. Obviously, switch frequency will be high. MOSFET do not require commutation circuit. You don't require any external circuit setup to turn it off. Using gate only you can make it turn off. Gate has full control over the operation of this MOSFET. Demerits. On-state losses in the MOSFET are high. MOSFETs are used only for low power application. MOSFET suffer from static charge application. High frequency and low power inverter. In inverter you will use a high frequency SMPS. In computer SMPS also they will use high frequency inverter and chopper they will use, low power AC and DC drive they will use. So we'll see what are the difference you can see in between BJT and MOSFET. This is the bipolar device, this is a majority carrier device. And controlled by the gate, it is controlled by gate. This is using base. Current control device, this is the voltage control device. MOSFET is the voltage control device and BJT is the current control. Why you can call this one as current control? In that graph now we have seen, if you want to switch your MOSFET from cutoff regions to saturation, you are increasing VGS. VGS means that is the gate to source voltage. But in BJT you can see that if you switch from cutoff regions to saturation region, you are controlling base current IB. Whenever IB equal to 0, then it will be in cutoff region. When IB is increased, it can be switched from cutoff regions to saturation. So because of this, MOSFET is voltage controlled, BJT is current controlled. Negative temperature coefficient, positive paralleling is difficult. Here it is very simple, parallel you can connect that. Losses are low in BJT. Here you have very high loss. Why? Just now we have seen in between drain to source, current to flow from drain to source, whatever the resistance that is offered by this MOSFET, no, that will be very high. But in BJT, no, to make that current to flow from collector to emitter, that resistance will be somewhat low. Drive circuit is complex, here it is simple. Switching frequency is lower than MOSFET, here it is very high. In MOSFET it is very high. BJT are suitable for high power application. For high power application you can use. MOSFET are suitable for low power application. For low power application you can use this. BJT are available with a high voltage and current rating. MOSFET have less voltage and current rating. Obviously you are using MOSFET in low power application, BJT in high power application. What are the university questions you may get? Draw and explain switching characteristic of power MOSFET. Just now we have seen. Application of power MOSFET. What are the merits and demerits? Switching characteristic, switching graph we have seen. Necessary waveform to explain switching characteristic. Transient model of MOSFET. Explain switching characteristic, that model, transient model with respect to switching characteristic you can explain. These are the university questions you may likely get. In next class we will discuss about IGBT characteristic. Thank you.